Okay, I think we're back. Hopefully. Yes, we are. Okay. Hi. So we finished the last video talking about how to extract element from matrices and how to pick out rows and columns and stuff like that. But in this second part, we're going to go through some of the math that we talked about last time. And we kind of hinted at this already. But, if I have a matrix that is 9, this matrix is 3 elements in the first row, 3 elements in the second row, 3 elements in the third row. This is a 3 by 3 matrix. We run that. Size of A, 3 by 3. Maybe I will do another matrix 4, 7, 3, oops, 1, 1, 1. I don't know. 2, 6, 2. Sure. 3 by 3. I run that. You can see A, E. You can see both these matrices that are each 3 by 3. So if I wanted to add them, I am able to add them because of the fact that they are same dimension. Oops. If I were to run this, let's write A and B first, A, B. If I were to run this, you would add the corresponding elements. So 1 plus 4 is 5, 2 plus 7 is 9, and so on. If you run this, 1 plus 4 is 5. That's the first row, first column element. First row, second column. 2 plus 7 is 9. 3 plus 3 is 6. 4 plus 1 is 5. 5 plus 1 is 6. 6 plus 1 is 7. 7 plus 2 is 9. 8 plus 6 is 14. 9 plus 2 is 11. I can do the same thing with differences if I wanted. Oops, I cleared everything. The differences are the same. 1 minus 4 is negative 3. 2 minus 7 is negative 5. 3 minus 3 is 0. 4 minus 1 is 3, and so on. So every element corresponds with a different element, or with the same element in the other matrix. And this doesn't have to necessarily be, 2, 3, 3, 3. This could be more than one matrix. I can do A plus B plus C if I want. And what we're going to get, the first element was originally 5, and I added one more to it. Now it's 6. So you can go ahead and add as many matrices or subtract as many as you want, as long as they're the same size. Oh, that's fine. Okay, so adding and subtraction. It's easy. Multiplication is basically the same thing we talked about in class. So for multiplication, we need the columns of the first matrix to equal the rows of the second matrix. I want to be explicit here. The number of columns, not the elements themselves, the number of columns is equal to the number of rows. Let's do an example. Let's say that A is 1, 2, 3. So this is going to be 1. This is the first row, second row, third row. That means that we're going to have 3 rows by 1 column. Yeah, we can check that. The only way to multiply that is if, we can write this out. This needs to be 3 by 1. The second one, if we do ultimately A times B, I'll leave that out for now. This would be 3 times of 1 multiplied by the B matrix. So how many rows does the B matrix need? Oh, remembering what we talked about in class, the number of columns has to meet the number of rows. That means the inner indices need to meet. So maybe I'll do run 1 row by 2 columns. Maybe I'll do 1, 4. This is 1 by 2. Right? I didn't go to a next row with a semicolon. I just wrote the elements across. That's going to be 1 row across multiple columns, in this case 2. So that means our final matrix should be what size? Well, we use the ones. Our final matrix is 3 by 2. So if we were to run this, before we even look at the answer, if I were to do size of product, I get 3 by 2, just by doing simple multiplication. And we can kind of see that math. Let's say we do, maybe I'll just do that as an example on the whiteboard. They're going to let me. Zoom changed its interface. I'm confused. Okay. Oh, look at this. Fancy. This is new. So the first matrix, A, that was 1, 2, 3, 3 rows, 1 column. And the second matrix was 1 row by 2 columns. I think that was 1, 4, right? Oops. Cool. Hope I didn't lose it. I didn't. Love it. Okay. Give me a sec. It's not letting me look at this. Where's my MATLAB? Okay, better. So if we were to go ahead and do A times B, A, which is 3 rows by 1 column, and B, which is 1 row by 2 columns, that will ultimately give us an answer. Let's call it C, that is 3 by 2. And what I would recommend is writing out the elements. So it's 3 rows, so C, 1, 1, C, 2 rows by second row, first column, third row, first column, and then there's 2 columns. So we'll just do it again. C, first row, second column, second row, second column, third row, second column. And forgive me, I'm writing with my mouse, which makes it kind of difficult. So what that means is if we look at C11, that's going to be the first row of A, which is just going to be a 1. I go back and undo. I can undo. Multiply by the first column of B, which is a 1. That gives us 1. C12 is the first row of A. Again, that's a 1. By the second column of B, which is a 4. C21. This 2 is telling us to take the second row of A, that's a 2, and multiply by the first column of B, which is a 1. C22. Second row of A, again, which is a 2, by the second column of B, which is a 4. We've got 2 more. C31. That is the third row of A, which is a 3, by the first column of B. That's a 1. And then again, C32 is the third row of A, which is a 3, times the second column of B, which is a 4. That gives us 12. So if we were to put this all together, it's going to be 1, 1, 2, it's a 4, 2, 8, 3, 12. 1, 4, 2, 8, 3, 12. Let's confirm that using MATLAB. Let's check. Shape screen share. Sorry. Yeah, I think we're right. Okay. So if we do this, 1, 4, 2, 8, 3, 12. So the moral is that as long as your matrices are the right size, you can go ahead and multiply them and it'll do that operation that we did in class. If you do the wrong dimension, so b times a, if we do that, that is 1 by 2 times 3 by 1. This matrix multiplication does not work because of the fact that the inner dimensions don't match. So if we were to try to run that, we will get an error. And it says incorrect dimensions for matrix multiplication. Check that the columns in the first matrix match the number of rows in the second matrix. And that's exactly what we'll be stressing in class, that the rows and columns of each of the matrices, the columns of the first and the rows of the second need to match. That's a very important point to note. Arguably, though, the most important thing in MATLAB, because matrix multiplication, you will do at times depending on the field you're in. But what's more important is that if I were to have two matrices that are storing elements and I want to multiply every element together, meaning I want to do element by element multiplication. An example of that would be, let's say I have, I can do this in the notes. Let's say I wanted to do F equals ma. I want to do Newton's second law, but I wanted to do it for multiple cases, multiple masses and stuff. So if I gave you this question on the homework 1, maybe you would have done M1 is 10, M2 is 3, M3 is 4, you know, a bunch of masses. A1 is 5, A2 is 20, A3 is 6, I don't know. Again, these are our masses. These are our accelerations. You know, and then you can go ahead and you would do F1 is M1 times A1, F2 is M2 times A2, F3 is M3 times A3. And these are our forces that are in newtons. And we could do this, you know, we can do that. And we can see that F1, F2, and F3 are all numbers. 10 times 5 is 50, 3 times 20 is 60, 4 times 6 is 24. Sure, that's fine. And it was really tedious. I know that you guys hated doing this. Another way you could have done this, you know, if you were to just do M is 10, A is 5, F is M times A, you would find the first one, then you would come back and you would change it to 3 and then 20. You'd find the second one. You come back again and change it, 4 and 6, and then you get 24, and you can do that to fill your table. That is very, very tedious and very annoying, and I hope that you kind of hate me for forcing you to do that, because I want you to remember the benefits of MATLAB. And the benefit is that I can store all the masses in a matrix. I can store all the accelerations in a matrix. And I can do element by element multiplication to find the 3 different forces. Let's say I do 10, 3, and 4. These are my 3 masses. And again, this is example number 6 in the notes if you want to follow along. A is 5, 20, and 6. So these are my 3 accels, 3 acceleration. And F is the product of them. But if you were to do M times A, it's going to give us an error because of the fact we're trying to do matrix multiplication when we use this operation. So this is a 1 row by 3 column. This is 1 row by 3 column. You cannot multiply them similar to what we did above. Plus, that wouldn't even give us anything physically relevant in this case, because what we're trying to do is multiply 10 and 5. That's the first M in the first A. 3 and 20, second M and second A. 4 and 6, M3 and A3. So the question is there a way to do that? And there is a great way of doing that, this concept of element by element multiplication. So for element by element operations, it doesn't necessarily have to be multiplication. It can also be division. Use a dot before the operator itself to tell MATLAB that you want to perform that operation on corresponding elements. And we're kind of hinted at this because once I ran this code, the one that didn't work, you know, incorrect dimensions for matrix multiplication, cool. The next sentence says, to perform element-wise multiplication, use a dot. These quotes are here just to show that it's, I don't know, you're referring to a specific operation. Ignore the quotes. Use a dot before the operation. So what that means is if I put a dot right before the multiplication sign, MATLAB is going to know that you want to do element by element multiplication. So I'll just write down M and A. If you were to run this, it is going to multiply the first element in each matrix together, the second element in each matrix together, and the third element in each matrix together to give you the final forces. So what you did in homework 1 by writing the same code, copy and paste it 3 times or changing numbers 3 times can be accomplished just by using matrices. It's really, really nice that it's able to do that. Another example I have in the notes is example number 7, which is based on density is equal to mass divided by volume. And again, you could do this for a bunch of different objects, one at a time, but it's much simpler to do it element by element. So I'm just writing down some of the numbers that I have in example 7. These are masses, maybe they're in kilograms. Volumes, 0.1, 0.5, 0.05, and 1. This is volumes, meters cubed. And then density is the mass divided by volume. But again, we want to do element by element. If we try to do this, it's going to give us an error. Well, it tried to do something that is not what we want at all. Honestly, I don't know what it was trying to do. We'll ignore that. But we want to do element by element. So to do that, we will put a dot right before the operator. So the operations division, we tell it to do a dot. It is then going to do 1,000 divided by 0.1, 1,500 divided by 0.5, etc. So if we run that, we end up getting the corresponding things. So 600 divided by 1 is 600, 1725 divided by 0.05 is this big number, and then so on. So by including the dot, you're able to do piecewise operation. So basically an element multiplied by the corresponding element. And that can be extended too if you wanted to do this across multiple rows. Just making stuff up now. I'll make them the same, so we'll get a bunch of 1s for simplicity. If you run this, you can see that it's going to take the first row, first column of each, the corresponding elements in each and divide them. And that is true for multiple dimensions. So 14 divided by 14, 20 divided by 20, 10 divided by 10, 100 divided by 100. If I wanted to confirm that, if I change 1 to 200, that final value should be a half. So if I run that again, oops. If I run that again, give me a second. It's not about trying to change the format here. Yeah, that's what we want. There we go. I don't know why the spacing is very weird, but you can see that now we have a half in that location, basically confirming that we're doing element by element division. Okay, the final thing is solving systems. And the first thing I think I mentioned during class last week, that you can solve systems very easily in MATLAB. In high school, you would do elimination or substitution to find those variables X and Y. And we discussed how we would write this as a matrix. Maybe our A matrix is the coefficients in front of the variable. So 2, 5, 1, -2. Our B matrix will be the answers. So if you were to write this out, oops, A, B, you have the first row, which is corresponding to the first equation. That's equal to 19. That's the first row of B. And then your second row is 1, -2. That's going to correspond to the second row of B. So really what we have here is something that is like 2, 5, 1, -2. that is multiplied by a matrix XY. See if I can do this nicely in MATLAB. I might need to write it on the whiteboard. Pretend that these brackets are long, meaning that X and Y are in one matrix together. This is one matrix. This whole thing is equal to 19. I don't like that. So give me a sec. Can I annotate on this? Oh, I can write on this. I'm learning so much, guys. So what I wanted to show was 2, 5, 1, -2 multiplied by X, Y. That is equal to 19, -4. And a very common thing that you'll see, is that this form here looks something like A times X is equal to B, where really these are our matrices. What am I drawing? Draw. So this would be A, this is a matrix, times X. This is a matrix. We're saying that X is the matrix of unknowns is equal to B. So I'll just write over here, matrix X is equal to all of our unknowns. There happens to be an X in here. But this could have been A and B, a bunch of random variables that we don't know. We typically generalize that as a matrix that's called X. Those are our unknowns. We don't know what they are. In theory, we just have A and B. So what you can do in MATLAB to find that matrix X, you can do an operation that is called the backslash operation. The backslash operation. The backslash is this one. I know we've joked in class how which is forward and which is back. This is typically called, A backslash B. And I know that the backslash from this operation is this. So I'm assuming that this is the correct nomenclature for a backslash. But if my matrices are properly defined and they make sense from a size perspective, and we know they do because we have the system of equations up here and converted it, I could say that A backslash B, that is equal to X. This solves the system. This operation here solves the system. So if you run this, you get this matrix X being equal to 2 and 3, where the first element is our first unknown. In this case, it's X. And our second element is our second row in this X matrix, which is Y. And if we were to come up here and check, 2 times 2 is 4, plus 5 times 3, that's 15. 4 plus 15 is 19. 2 minus 6 is -4. So just by having an arbitrary system of equations, we can end up solving for that unknown variable. It's really, really useful if you're trying to solve a system. And you might have systems that are crazy. I'm just going to make up stuff that doesn't even make sense from like a mathematical perspective. I'm sure that there are, or 8, not 8. I'm going to make different numbers here. -4, 1, 5, and then 2.5. I don't know. And then B, and I'll explain what this means in a second. So really what I have here, I guess what I'll do first is I'll show these. That's A. So you see that I have a system here that's basically 3 equations with 3 variables, and they are all equal to that. So maybe I'll write that as, I don't know, I'll say that it's M I'll use different letters in X and Y, plus 2n plus 3p, that will be equal to 10 based on this row and that row. Then I'll have 4m plus 19n minus 4p, that's equal to 32. I really hope you guys can see this. I'll be so mad if you can't see it. M plus 5n plus 2.5p, that is equal to 8. So this is a system of equations. They are linearly independent of each other, and we may talk about more of this in the future. Basically, what that means is that they're completely separate. One is not a multiple of another or anything like that. So what that means is that I should be able to find what Mn and P are. So Mn and P is equal to A backslash B. If I were to run this, it does give me, where's that X? I'll ignore that X. Oh, it does give me the same thing. But if I run this, it gives me these 3 random numbers. Again, I made this up. This is not a pretty system of equations, but M is equal to 11, B is equal to this negative 0.65, and P is equal to this 0.047 or whatever. So it's really powerful. You can have a system that is, hundreds of equations, and it'll do what it can to find the values of your unknown variables. Okay, that's probably good enough for now. We will talk more about this in class. I encourage you to message me if you have any questions. Oops, my video disappeared. So annoying. Okay, well, stop sharing. Oh, there you go. It was still sharing. Okay, I'll see you in class on Monday. Please let me know if you have questions. Thanks.